you please welcome Professor Kojiyama with a round of applause for his presentation?
Thank you very much, Professor Kim. Good morning, ladies and gentlemen. I'm Kazuya Tomiyama of the Ministry of Technology. It's a great honor to be here and present our research in the plenary session of this great conference. Today, I'd like to talk about the contribution of dual-tree complex wavelet to three-dimensional analysis of pavement surface. Actually, I'm working for pavement engineering, so I'd like to talking about a little bit about the contribution of dual-tree wavelet to the pavement surface evaluation. Okay, my presentation consists of 5 parts from background to the future works. Okay, let's begin with the introduction. As professors of the University of Tokyo have introduced, strategy for the eye construction is vital to improve the productivity of the construction in Japan, and is also important to the pavement engineering field. We, in the pavement engineering field, promoting eye construction for the design and construction, quality control and quality assurance, as well as the maintenance and rehabilitation integrated by use of the information communication technologies. In these strategies, the 3D data set are normally used instead of the conventional 2D measures to improve the productivity and to improve the construction quality as well. So now, as you know, we can easily access the 3D datasets, 3D point clouds by using the ITC devices like laser sensors or UAV. So we can use such kind, when we use such kind of data, the data includes much information rather than the traditional 2D based measurements. And then it can easily detect the localized irregularities with a millimeter precision. And now laser sensing technologies has a high accuracy and high precision less than the millimeters, and we can easily assess the tiny irregularities on the pavement surfaces. However, it's still challenging to identify the information required. I mean, the functional perspectives of the surface characteristics. Let's say the interaction between the vehicle and surface conditions. So we need to make a relationship between such kind of functional perspectives of the pavement surfaces and the physical properties measured with the other point clouds. So we, in this research, introduce the mathematical analysis with dual-tree complex wavelet transform. It's quite interesting to analyze the 3D point clouds data. It will achieve the effective and efficient data processing for 3D dataset with non-linearities. And it can diagnostic identification of the pavement surface in terms of wavelengths, locations, and direction of the irregularities, which means the functional evaluations can be made. And in the background of this research, we need to clear evidence and theoretical evidence of the analysis. Okay, so the research will be based on the theoretical background of the wavelet. Okay, so the first of all, I'd like to talk about a little bit about the theory of the wavelet. The theory of the wavelet is very simple. The original signal, including point clouds, can be divided into 2 elements, such as approximation and details. And the approximation can be divided further into the following approximation details using a small localized wave called wavelet, as shown in here. The shift of the wavelet and the scaling of the wavelet can be make this kind of multi-resolution analysis. So, according to this feature of the wavelet, it can make implementation of spatial and spatial frequency analysis as a function of the distance. In case of the function of the time, it can be called as the time frequency analysis. So the wavelet has been used in many applications, including 3D data like photographic image processing, and the most famous one is the fingerprint recognition in the Federal Bureau of Investigation in the United States. It involves the wavelet analysis to identify the fingerprints. So we try to apply the wavelet, relatively new wavelet, duality wavelet, into the pavement surface measured with 3D equipment as point clouds. Okay. So in addition to the conventional discrete wavelet called DWT, the new wavelet called duality wavelet involved the imaginary function of wavelet and scaling functions, as same as the conventional Fourier transform, as shown here. And it uses two types of wavelet. One is the real number wavelet, and the other one is imaginary number of wavelet. According to this feature, the approximately shift invariant tree transformation can be achieved. As shown here is the actual same shape step functions with a little bit offset in longitudinal directions after the decomposition using the conventional discrete wavelet transform and duality wavelet transform, as shown here. In case of the conventional wavelet, some steps are distorted according to the location, as shown here. Exactly the same, the shape is exactly the same for every location, but DWT cannot make it. In contrast, the duality wavelet can decomposition with the feature of shift invariant, as shown here. The shape is almost the same for each location. So this is very strong. This is very strong to analyze the irregularities of the pavement surfaces, like pothole or the artificial structure like manhole or utilities or something like that. Okay, another feature of duality wavelet will be directionality of the decomposition. Actually, the conventional duality wavelet has 3 directions for vertical, diagonal, and horizontal. In contrast, the duality wavelet has more directionality, as shown in here. And there is no aliasing effect. It means in case of the conventional one, includes some artifact called aliasing in the diagonal directions, as shown here. You can see the checkerboard flag shown here. But the duality wavelet doesn't make the checkerboard artifact. So this is also important to analyze the pavement surface with 3D measured data. Okay. Okay, yeah, you can clearly see the checkerboard artifact in the conventional wavelet. Okay, so let me show you an example and the strong point of the duality wavelet. The block pavement is a good example to prove the strong point and the advantage of the duality wavelet. We arrange block like as shown here. This is normally used for the pedestrian zone. So we measure this using terrestrial laser scanner TLS. This is a typical tool for the construction strategies, and there are many all of those contractors or road agencies are using this kind of devices. And the measurement setup, as a measurement setup, the scan density was 3 millimeter at 10 meter location. This is enough to detect the small irregularities, including the joint of the block and some fault of the edge. And then the coordination accuracy was 1.9 millimeter at the 10 meter location. This is also enough to the application of pavement engineering field. And as a pre-processing, we use the mathematical coordinate system rather than the geographic coordinate system to understand easily of the advantages of the directional analysis of the wavelet. And the point clouds are normally inconsistent between the point by point, so we resampled the measured point cloud at the interval of 1 millimeter. Okay, as you can see here, the actual measurement result looks like, and left-hand side is a photographic image of the blocks measured, and the right-hand side indicates the laser intensity. The laser intensity is a bit important to see the joint conditions of the block pavement. But there are no information about the elevation. Okay, so firstly, then we normally draw the heat map as shown here. As you can see, the heat map, there are some slope, some design grade from top left to bottom right. Yeah, it can easily identified by using this heat map, but we cannot identify any surface irregularities like the condition of edge or condition of the joint or something like that. So we apply the multi-resolution analysis using a dual-tree wavelet as shown here. So according to the result of multi-resolution analysis, we can easily identify the irregularities. We can see some irregularities in a specific wavebands. For example, the edge deterioration can be seen in the level 4 shown here, and the joint fault can be seen in the level 5 to 9. Okay, as you can see here, some edge, something wrong in this part of the edge. Okay, we cannot see this fault in the original heat map. And level 9 to, level 7 to 9 indicates the unevenness, which means the undulation of the block arrangement. Okay, so here is the little bit convex, and here is in the concave. Okay, so actually, we carefully take a look at the condition of the block. Here, some block are a little bit deviate from the planar surface. This is a tiny deviation from the designed plane, and it cannot identified using the original heat map. But after the decomposition, as we see in the multi-resolution analysis, we can easily identify the condition of this block as shown here. This is the only directional result. And this figure, the data are integrated into the one point clouds. The level of 4 and 7 to 9. These levels are related to the deterioration or deformation of the surface block pavement, and we integrated them into the one point cloud as shown here. And the dual-tree wavelet can also make a directional analysis as shown here. So as you can see here, the deformation is occurred for the longitudinal direction shown here. Okay, so actually the traditional wavelet DWT can make the same analysis as shown here. The results are similar between two analyses, but as I mentioned, the original conventional wavelet includes checkerboard artifact, as shown here. This is a strong artifact. It may misunderstanding of the surface irregularities. On the other hand, the derivative wavelet are include less artifacts compared with the conventional. Okay, let me summarize my presentation. In Japan, the reconstruction strategies are accelerated to minimize the resource and efforts and maximize the outcomes. Okay, in Japan, as one of the Asian countries, so we needed to improve the productivity in terms of such kind of the human resources. And it will improve the productivity, not only productivity, but also the quality of the design, construction, and maintenance and rehabilitation using ICT devices. And in this study, we expand the 3D measurement of pavement surface, introducing Wavelet. Okay, so this kind of 3D data includes much more information compared with the traditional 2D based measures. And it will enable us to make effective and reasonable processing of a pavement surfaces. Normally, the pavement evaluation are done with empirical knowledge. Okay, so the derivative wavelet will contribute to solve the shift variance problem in the conventional wavelet, and then will achieve the shift invariance directional multi-resolution analysis. And according to this research, as a result of this research, we can easily understand the deterioration mode in terms of the wavelengths, locations, as well as the directions of the irregularities. It will realize the area-based quality assurance of the pavement, especially in the pedestrian zone. The road users are moving around everywhere instead of the roadway. The roadway is only linear movement occurred, but in contrast, in the pedestrian zone, the road users can go everywhere. So it will improve the investigation for the functional assessment of pavement condition as well. Okay. So finally, I'd like to talk about a little bit about the future works of this research. The intention of this research is actually focused on the pedestrian zone, as I mentioned, instead of the roadways. And we use the 3D data, of course, and we also involve this kind of measurement systems like the muscle reaction of the road users. And we sometimes measure the physiological information, including heart rate and or some human skin conductance, like the sweaty or something. Okay. So we are now trying to evaluate the pedestrian, wheelchair users, and wheelchair mobility. And now the bicycle and the e-scooters are many popular all over the world. So we are trying to evaluate the pavement surface for these users. Okay. Thank you very much for your kind attention.